Shall we start, sir?
Yes, sir.
Okay. Bhaskar, I request Bhaskar to start the session. Thank you.
Yeah. A very good evening to one and all gathered here. It's my pleasure to welcome you all for the day three session of this Atal Sponsor 60 online FTP on recent advancements and challenges in integration of IoT and 5G or 6G wireless communication for building the next generation connectivity. Welcome you all. And it's my great pleasure to welcome our today's resource person, Mr. A. Manimaran, sir, Manager, BI Solutions, Bangalore. Welcome you, sir.
Yes, sir. Thank you, sir.
Yes. And like from organizing committee, like there is one instruction for all the participants. The- as we said earlier, each and every session attendance is mandatory, and we had updated the last 2 days attendance in your ACT Atal portal. You can crack your attendance percentage over on your portal, and you may check. If you find any deflections over there, you may contact the coordinators through WhatsApp. While sharing your details, you should share your name, email ID, as well as your Atal FTP ID with the coordinator. Then we can able to track your records. Okay, thank you all. And as per the procedure, uh, before moving to the session, we have a common photography part. So for that, we request all the participants to take turn on a camera and with our resource person itself. Thank you all. And before moving to session, let me say short intro about our resource person. For this, I request our organizing committee member Nandakrishnan to hand over.
Participants, you can turn off your video. I'm very happy to welcome our today's resource person, Mr. A. Manimaran, Assistant Manager, VA Solutions, Bangalore. Mr. Manimaran graduated as a BE Electronics and Communication Engineering from Anna University, Chennai. Currently, he is designated as Assistant Manager in VI Solutions, Bangalore, and handling major responsibilities for supporting various industries in implementing several turnkey systems and system integration projects using NI products. He also handling major responsibility of improving the quality of engineering and science education and eradicating the improvised methods of education and incalculating the interest of lab view. He has traveled far and wide throughout the India and Sri Lanka, has delivered provoking lectures with inspiring the students and kindle their interest towards LabVIEW, and also visited more than 200 Indian engineering institutions. He also conducted many faculty development workshops on various trending technologies, including RF communication, wireless systems, advanced signal processing, and data acquisition. He has delivered more than 350 lectures on engineering education on varied technology topics. His area of interest is RF communication, wireless systems, measurements and automation sensors, data acquisition, signal conditioning, wireless sensor networks, FPGA based embedded system, and so on. Now, I would like to call upon Mr. Manimaran to take over the session. Please, sir.
Thank you, sir. Thanks for the introduction.
Thank you,
I'll
sir.
just share my slide.
Okay, sir. You can share your screen.
Part, how would it be and how we can take it. So just let me know whether you get my screen there.
Okay, sir. Okay, sir. You can start sharing your screen, sir.
Sir, is my presentation visible?
Yes, sir. Your presentation is visible, sir.
No. Fine. Yeah, thanks.
Okay, sir. Thank you, sir. You can start now,
Okay.
sir.
Sure, sir. Sir, fine. Very good evening to all. I know it's very late of the day. We are starting the session. Uh, but quickly, we'll just get into this. Sir, can you tell me in between? Do we have any break of 5-10 minutes time in between till 7:30, or we can have a single session together? Hello.
Sir, there is no break, sir. You can.
Okay, fine then. Great. So we'll try to close it as a single stretch. So to everyone, if you have any queries in between, please do let me know. You can stop me anytime so that I can we'll discuss on it. And in chat also you can drop in so we can discuss things over there. So I'll just go for the slideshow here so that the maximum screen will be visible so that you all can see this. So this
Sir,
particular
it is.
sections, what we have here as a software defined radio. I'm sure most of the professors who are working on an RF platforms or who are doing researches in RF, they'll be aware of this software defined platform. In National Instruments, we have a SDR hardware. We used to call it as a USRPs, software defined radio. So basically, what this software defined radio is meant as, software defined radio is something as a generic hardware platform which is used to implement any kind of radio functionalities. For example, if I want to tell you, we have something as a normal breadboard which will perform all kinds of circuit operations. For example, for every simple amplifier, you will be rigging up different circuits over there. For example, if I want to put it for a same board you will have, where you will be running on a class A amplifier, and you remove it and you will be defining it with a class C amplifier over there. Or if you want to make something as an FM transmitter, you will rig up a circuit. If you want to have an AM receiver, you will rig up a circuit. If you want an AM modulator, you need a circuit. If you go for a FM demodulator, you will have a circuit. So similarly, if you see, we were trying to do something on a generic breadboard where you rig up things over there. But here what will happen is, we'll have something as a hardware which will do everything out of it. But that will be defined by the software. That's what it means there. So our SDR will perform all functions. It can act as a transmitter, it can act as a receiver, it can act as AM, it can act as an FM, it can act as ASK, it can act as FSK, PSK, modulator, demodulator, everything it will do. But how we are going to define it, that's what it would be. So if you see here, we have something called as USRP hardware. We have a transmitter and receiver here. So with this kind of software defined radio, we would be defining the hardware to behave as a transmitter. So it will act as a transmitter. Earlier, we used to have something as a traditional boards or kits we will have in our colleges, where only one particular application will be done on it. For example, if you want to do something as a PCM, then there will be only one module which will do the PCM there. If you want to do something as a AM modulation part or encoding or decoding, you need to use a different board. So what we will do it is we used to connect multiple blocks together to build this application in order to get a single transmitter section or a receiver part over there. So similarly, what we are going to do it is in this particular hardware, our hardware will only act as a transmitter or receiver. The software is the portion which is going to define what kind of work it's supposed to do. Here I have kind of shown USRP which interfaces via Ethernet. We have USRPs which interfaces via USB also. Directly plug and play type, you can use it and you can move on there. Or even highest standards also, you have PCI, PXA formats, standalone devices you have over there. For example, if you see I have a modulation, I have a demodulation process, I have a digital and analog up conversion and down conversions. If you see that RF portions only is happening at our hardware level. The rest of the modulation, demodulation, signal processing, filtering, reconstruction of your signals, your input data, everything will be defined by your software. That's why it is called as a software defined radio. So now I'm going back to the different kinds of elements here. So now in this particular, if you see, I have USRP hardware, which is a model of 2920 that works within the range of 50 megahertz to 2.2 gigahertz. This interfaces via Ethernet. I'll show you one more hardware. I'll just show it through my screen here. So I have a USRP 2901. If you see here, I have a two RF channels here. There we had only one RF channel. Here I have two RF channels in it, which means two daughter boards are present in a single hardware. This is a USB based hardware. The same model, we have it in a 2900. So what we have it is, this will be as a single element, which is of a USB based hardware there. So I just want to show you the difference between the number of channels what we have here. So if you look at in this, we have one RF channel. We have two RF channels. And in our slide also, I have one RF channel here. So this is of Ethernet. The latest modules what we have, it is of USB models here. And if I want to showcase you the difference between, this goes with 50 megahertz to 2.2 gigahertz. But these small cards what you have, it works from 70 megahertz to 6 gigahertz it will work. So if you want to work on any frequency levels, if you want to work on MIMOs, or if you want to work on any GSM bands, or if you want to work on any higher data transfer rates, or if you want to work on a radar level to on a sub 6 gigahertz, if you want to work on it, you can easily work on these models over here. So I'll just go with this. I'll explain you how these would be there. So in this particular, if you want to synchronize this hardware with an existing system, you have a reference elements where you can synchronize it. So I have one TX and one RX here. So I'll explain you in the back end how exactly it would be. So this is a block diagram of the element. I'll open it in a new page, so where you can see things here bigger. So if you see this particular, I have connected via Ethernet to the PC, and this has one transmitter section and one receiver section. I don't have two receiver section, I have only one receiver section. Sorry. So if you see here, I have a PLL and VCO dedicated for transmitter portion. I have a PLN VCO dedicated for a receiver portion, which means I have this particular hardware can transmit at any frequency between their working range. This also can receive any signal within that range, which means it is a full duplex system. So it can transmit at X frequency, it can receive at Y frequency. It can transmit a video signal, it can receive an audio signal, both can happen at the same time. There is no restriction, only transmission should occur at once and reception should occur separately. No, nothing as such. So we can easily work with such kind of devices. These devices are full duplex. And if you see over there, we have different models which will of different working ranges we have. These are all the little old items of limited options you had. Now you have a very sophisticated systems which starts from 10 megahertz to 6 gigahertz we have. Higher end models we have in it. That also you can connect via Ethernet and you can work on it for a higher data rate and you can work on them. So different applications you can use with it for a GPS or a FM radio options or OFDM or a radar, or if you want to use it as a spectrum analyzers, if you want to tap your data and you want to check that, yes, you can use that. But this will only act as your RF front end. You cannot see this RF signal in this because this will act as a RF down converter as this information shows. So it will convert your analog signal to digital and it will give you a complete digital data. You cannot see the RF spectrums of this. In order to see the RF spectrums, you will require a spectrum analyzer there. Within that particular band of frequency elements, how many data you are sending over there, those things, yes, you can monitor and you can see here. So any doubts so far in this particular USRP hardware? I'll further proceed with this block diagram once again. But so far, do you have any queries?
Participants, if you have any queries, you can discuss with the resource person. I repeat again, participants, if you have any queries, you can discuss with the resource person.
Okay, fine. Yes. Yes, ma'am. You have raised Asha, madam. Are you available? Okay, fine. So if you have any queries, just drop in over there. So in comments. So what you can do it is, if I tend to see, so probably at the end of the sessions also we can continue over there. Fine. So now, if you see here, as I have mentioned very much earlier here, and the last one, I have a transmitter section which has a separate PLN VCO. I have a receiver section which has a separate PLN VCO here. So it is a complete full duplex system which is connected to my PC to pass data over there. So only option now we have to do it is, now we have to define a data and we have to tell in what format of transmission it has to go into the transmission channel, so that it will get into that particular communication path. So whether it is your what modulation schemes you are going to use for it to send it over there and to get it, or if you're going to plan for MIMOs, how exactly you are going to keep multiple transmitter and receivers to get in, that we have to define it in a program part. But hardware wise, this is the one. You will have one TX and one RX there. You can define your data. Your data can be your any signal data, or it can be your image data, or you can connect your camera to your PC. You can take a video and you can transmit video also to it. So no problem with that. You can easily do that. So now there is a sequence to define your hardware there. So initialize, configure, start, read or write, stop and close. So this read or write will be in a loop for continuous operation. So if you're defining something over there, to which channel you are configuring them. So that's what we are defining there. So through which USRP you are connecting. I have connected via Ethernet. So there is an IP for it, 192.168.10.2. So you can connect multiple USRPs and you can define them with an address and you can move on. And what rate you are transferring your signal there, and how good content you want to process, and your hardware has to do things and you want to push. So those things you can define over there in it. And what is your RF carrier frequency you are trying to push this data there, so that your data will be available for others at that particular frequency. So if you are transmitting at one hardware at a particular 915 megahertz or 1.25 gigahertz, and you are receiving that signal through another USRP, you will be tuning to this particular carrier frequency to view it. Or if you are configuring this USRP for receiver purpose as something as an FM demodulator, you will write a program as a FM demodulator in your software, and your carrier frequency will be your FM station frequencies. So either it will be 100.5 or it will be of 93.8 or 93.5, any frequencies you can have, and you can take with it and you can work on. And through which antenna you are trying to read, whether you are receiving through an RX antenna 1 or 2, or if you have multiple receivers through which you are trying to take, what should be its transmission gain and what should be the receiver gain, you can define and configure, and you can do the transmitter options over there. So you can define it with how good signals you are expecting to receive. So if you are using a single system to transmit and receive, then it is of very close. But when you are going for a different distance, then what you're supposed to do it is, one is for a smaller antennas, you can have a line of sight and you can achieve it. Or depends upon the power of your antenna and your antenna strength, how much you can transmit and receive, your signals qualities will be there. So I can get into the other one. So there is a simple option how you do with your digital communication methods with USRP here. If you see, these are your software options what we develop over here in LabVIEW. But in this software portions what you develop over here, our USRP will come into the place of up conversion and down conversion, because our USRPs will only act as a up converter and down converter. It will not do any work other than up convert and down convert, because the rest of the modulation and inputs to your signal, everything is defined by your software there. So in your programming part, all your data will be defined in a software where we have dedicated icons in LabVIEW to do this there. So you can define your bits, you can generate some simulated bits, and you can push in place of simulated bits. What you can do it is, you can put your actual content text, you can write, you can put your what to say, any of your signals you can transmit over there, or any of your videos you can share. If you convert your image into an array of bits, that also you can push and you can move over there. So since this up conversion and down conversions are there for software simulation, once you go for hardware, then what will happen is this USRP will replace your up convert and down convert option. Rest of things are same. So till this, any doubt? Because after this, I'll just start with a small program in LabVIEW and show you how you can do this modulation schemes with the simulation and how you can use with this.
Participants, if you have any queries, you can discuss with the resource person.
Sir, can we use single USRP for transmission and receiver?
Yes, you can. Because if you see in my slide, I have a single USRP only, where I have a transmitter and receiver there. This individual USRP has a one transmitter section and one receiver section. That's what I have shown you in the block diagram of this hardware. The top portion is a transmitter section. The bottom portion is a receiver section. So if you put an antenna there, which will be a wireless transmission between your TX and RX.
Okay.
If you put a wired cable with an attenuator, then it will be a wired transmission there.
Okay, sir.
If your
Thank you.
hardware has only transmitter, then you need two devices to do that. One simple example is earlier what we do it is we will rig up a separate transmitter portion there. Modulator section we will have separate, demodulator section we will have separate. Now what we are doing is in a single hardware itself, this everything will happen there. What is the impact of frequency in selection of USRP? So Subhashni ma'am, impact of frequency in selection of USRP is, can you be more specific? Are you looking for on your application wise? Because it is something as I can understand. I'm understanding in a way. Please correct me if I'm wrong. Impact of frequency in selection of USRP is, see, I have shown you two different USRPs here. So for example, I have USRP 2901. If you see, I have a software defined radios. I have a different software defined radios over here. So now one is there at 30 megahertz to 4 gigahertz and 1 megahertz to 7 gigahertz. Now the choice is to me which one to choose. If you are asking me to go with 70 megahertz to 6 gigahertz or 10 megahertz to 6 gigahertz, I'm going to choose this USRP whether I am going to work on which particular frequency. Because USRP has a different options. How exactly when you go to a normal shop, you will have a different ranges of battery or your LED bulbs. So you have it at 24 volt, you have it as a 90 watt also. But that depends on how much brightness you need, how much I can say it as what is your requirement, based on that you can choose. The impact of frequency in selection of USRP is in what range you wanted to work. Second thing is, if you see in my screen here, there is something mentioned as a bandwidth here. I have a two different hardwares here, 80 megahertz bandwidth, 1.6 gigahertz bandwidth, 400 megahertz bandwidth I have. So which means what I have here is the amount of data it can process within that hardware part I can take here. So few elements, whatever I have in this, depends on the model and the options. I have a different working ranges and the memory part of it to work on it. In that way, this impact of frequency in selection of USRP matters. So if you're working on a low frequencies, you can choose your working range over there. You may not go and choose a hardware which works from 10 megahertz to 6 gigahertz. You can go for a 70 megahertz also. Hope I answered your question. Thank you, ma'am. Thanks. Shall we proceed? No queries up to now.
Participants, if you have any queries, you can discuss with the resource person. I repeat again, participants, if you have any queries, you can discuss with the resource person.
Hello, sir. I
Yes,
have a
ma'am.
question.
Yes.
Question is, this is NI-based LabVIEW software, right? So in
Yes, ma'am.
this, we will be writing the program for
Yes.
whatever operation we want to perform using SDR. So
Yes.
which language is basically used here?
See, actually, now I am going to use LabVIEW.
Huh?
This particular hardware, whatever I have shown, is an NI make, National Instruments make.
Okay.
So the same hardware which is available in ETS research also. This
Okay.
ETS research is also an NI USRP only. It is actually ETS Research is again an NI company. Do you see it is
Okay.
an NI brand? It is the same hardware what I have.
Okay.
So
So hardware and software both is from NI.
yes, hardware and software both are from NI. These hardwares also are SDR hardwares.
Okay.
So if you see, I have a one channel, I have a two channels over here in this. So these hardwares are generic USRP SDR hardwares. These SDR hardwares can be programmed using your GNE radio. Even NI
Okay.
hardwares also support GNE radio. It is not only mandatory you should use LabVIEW. You can use
Okay.
GNE radio also to use it. And one more additional information since you have come up with, even you can use MATLAB also to program NI USRP hardwares. Yes, MATLAB also
Yes.
has few good supports for NI USRP devices.
Okay, okay.
As
That's
soon
what
as
I
you
wanted to ask because we are having one SDR in which
yes,
we using MATLAB. So
yes,
since I was not aware about this NI LabVIEW based SDR, so that's why I asked ki which particular language you will be using for programming. Fine, sir. Thank you. Yes,
yes,
GNU
ma'am.
radio and MATLAB. I'm aware. Okay, sir. Thank you.
Any
Thank you.
radio, MATLAB, LabVIEW you can use because if you are going with NI based USRP cards or ETS based USRP cards, there is
Hmm.
something called as UHD drivers you will get.
Okay.
Universal hardware drivers, which is for USRP
Okay.
hardwares. So USRP hardware drivers, UHD, that will support GNU radio programming as well. Uh, LabVIEW also will be supporting with that. You can directly program with that.
Okay, sir. Okay.
And any
Thank you.
SDR hardware, third party, if I want to tell you, Keysight also has a make in SDR. Keysight will give you hardware driver in LabVIEW so that I can program that make also in LabVIEW programming.
Okay.
So different makes different companies does. Even analog also you analog devices also you have a hardware called as Pluto. Different
Okay.
materials you have, man. It's all depends on how convenient you are and how comfortable you are in developing applications there. I'm comfortable with developing applications in LabVIEW, so I'll just go with LabVIEW there.
Fine.
So if you are familiar with using GNE radio, yes, you can do.
Okay, sir.
Same MATLAB, if you are using Simulink to program, yes, you can do. Choice is yours.
Okay.
So
Thank you. Thank you.
yes, ma'am. Any other doubts? Okay, cool. So I'll just go to LabVIEW. I'll just start simple codes for modulation schemes. So if you see here, I'll just created a LabVIEW program. So I have a front panel and block diagram. How exactly you have a coding portion here and visualization portion over here. So what I'll do it is, let's say I'm just going to define one signal here. So I have my signal. So this is my message signal here. So I'm going to define my message signal as a sine signal. I'm going to keep some frequency, amplitude elements I have there in it. I'll say OK to it. So now what signal I'm going to generate, I'm going to keep my message frequency. So I create a control for it. So this is a message frequency over there. So now in this message frequency, this is going to give me a signal. I create a graph indicator. So if you see over there, whenever I write, so I have generated one signal over here. I have one sine wave here. So this message signal, whatever I want to visualize, whatever I want to showcase here. So now what I'm going to do it is, this I want to pass through some modulation schemes and I want to take it. So what I'll be doing is, I'll go to RF communication palette. I have different options here. If I want to work on modulation schemes, I have a modulation palette analog and I have a digital modulation schemes where I can work on it. If I want to work on spectral measurements, I have a different spectral measurements. I have a adjacent channel power, all RF spectral measurements options I have there. I'll just get into modulation, analog, modulation, AM, FM, PM, up convert I have. In demodulation, I'll have the reverse, down convert, demodulate, FM, PM, AM I have. So I'll go with the same slide sequence over here. If you see in this, I'll have a source coding elements. I'll upconvert, modulate, and give over there. So these all elements, whatever this. See, you cannot go with different types of uh, uh, what to say, different source codings or channel encodings. You can choose with your own choice. Modulation schemes I'm just choosing here. So I'll just go with communication, modulation, analog. Modulation, I'll take AM modulate. I'll keep here. So this is an AM modulation icon. So message modulate. So to this icon, I press Control H. So this requires a message signal. So it will give a modulated data. So now what I'll do is, this is a message signal. I'm feeding over there. So now here I want to define the modulation index. So M value greater than 1 or equal to 1 or less than 1, I can define. So whether it is a double sideband or a single sideband, I can choose here. SSB or VSB, I can define there. So here I'll create a DSB. I'll create a control for suppressed carrier. So what I'll be doing here is, here in this portion, I'll be taking it as a modulate AM icon. So here, whatever I see this output, it won't be a modulated output because there is no carrier frequency involved. Carrier frequency come into picture whenever you're going for an up conversion part. So RF communication, modulation, analog, modulation, up convert.
Sir, may I know this is which type of simulator, sir? I am unable to understand.
This is a LabVIEW, ma'am.
Okay, sir. Okay.
This is LabVIEW software by which I am using it. This is not a simulator. It's a simulation kind of it, but it is a LabVIEW software which I'm using to showcase.
Okay. Okay.
You can use MATLAB also to do it. You can use GNA radio also to program the same. So if you see here, this is going to give me one modulated waveform. For up converted, I need a modulated waveform so that I'll get the final output there. So if you see here, modulated output, I'll feed as an input here. After modulation defined, I'll give it to an up convert. Here I have a carrier frequency. I create a control. So I have a carrier frequency here. So now I have a message. I have a message frequency. I have a carrier frequency. I have a modulation index, everything I have. So now if I want to see the output, so I'll have a copy of this graph. I'll make it as a AM signal. So now what I'll do is, I have an AM signal here. So I have a message signal. I'll just keep this small. I'll make the AM signal big so that we can see things clearly here. So yes, I have this informations. I'll replace these elements with primary control. So I have a suppressed carrier, modulation index, separate. I have a message frequency. I have a carrier frequency. I'll try to make them big so that it will be visible to all. So hope it is visible to all. So now for message frequency, I have a carrier frequency. So now if I run it without any carrier frequency, I'll get as the same. So now what I'll do it is, I'll just keep somewhere 300. I'll run here. So now if you see, the shapes are not good. Though it is an ideal modulation, I'll try to go for multiple, 10 times of my signal if I try to keep. Do you see the shapes are not quite good over there? This is because of the samples what we are using for our signals are very less. Only 1,000 samples what we are trying to generate a signal. I'll go for more number of samples. So what I'm going to do it is, I run this program. So now I'll get a proper shape. So now if I want to show the envelopes of it, I want to compare my message signal with the modulated output signal. I'll just take the signal, I'll put a join over here. So if you see, I combined two signals here. So I'll get two signals there. So now if I want to show the reverse of it, I'll take a negate of it. So positive signal will become a negative signal here. So I'm enclosing my message signal, the original content. This is the original message, what I have, which I'm feeding to it to compare, which is acting as an envelope between both for my modulated signal there on both the sides. So now if I run it, so I'll get both the sides there. In order to showcase very clearly, line width, I'll keep here. Both I'll keep white color. So its visualization will be much easier. So this is an envelope. One is or to be differentiative. Okay, negative line, I'll put it as still a green. So wherever you have a positive cycle, it is modulated. When you got a negative cycle, there is no modulation there. And this is what you have the modulated output in between what you have there. So now I run this continuous. When this is of 0.5, there is under modulation. So you can go for any frequencies you can take and you can define them there. So if it is of over modulated, even in the negative cycle also you have some portions are getting there. So when you go for suppressed carrier, you cannot see any differences there. Because what is this suppressed carrier? How you define them to your students when you do over there? In a very simple form, what I'm going to do it is, if you see my modulation index value is getting added to the amplitude of my signal. So here I remove this auto scale, which will not vary. So I run this program, suppress the carrier in the sense my carrier signal will get suppressed within the limits of my message signal. So whether it is ideal modulation or under modulation doesn't matter. I cannot see any differences there. So if I want to visualize them very clearly there, so what I'll do it is, to this AM modulated output, I'll just go to a signal processing, signal analysis. I'll take a spectral measurements. I'll keep over here. So I'll take a pause spectral density linear. So I'll get only a peak. So here you can apply any type of filtering. Rectangular is none. By default, if you choose none, rectangular window will add to it. So you can choose any kind of your filters. I'll add to it. So this is my AM modulated output. To the AM modulated output, I'll take an FFT here. Just a graph I'm copying. I'll say FFT there. So I'll get an FFT there. Yeah. I'll just pull them up. So now I run them. So here, if you see here, I have one peak where I have my carrier frequency 300. So when I keep 500, my carrier frequency, I'll have a center frequency at 500 there. My message frequency at 20, it is very close here. So what I'll do it is, I'll keep somewhere 700 as my carrier frequency. I'll try to keep somewhere as 50 as my message frequency. So I'll just zoom this portion. So that you could see the signals over there. So 700 to left side 50, right side 50. 650 I have one peak, 750 I have one peak, double side bands. When I say suppressed carrier, carrier is suppressed. There is no suppressed carrier. Carrier is not there. So suppressed carrier you can easily do with that. So this is DSB signal. This is DSB SC signal. You can easily visualize there. So very good things. You can visualize things and you can showcase it to your kids when you do there. So now modulation portion over these three icons with these two icon. Now if I want to demodulate, what I have to do, I have to go to this block. modulation, analog. I did modulation. Now I go to demodulation. So I'll go to demodulate. Okay. But before I demodulate, I should receive the signal through an antenna. So how I did up convert, I should do down convert. Then supposed to do demodulate AM. So these two icons which I'm gonna use. So first, whatever I'm gonna keep. So after up convert, I'm gonna keep down convert. After down convert, I'm gonna keep demodulate. So now whatever is being up converted, whatever is being transmitted here through my antenna, that I'm receiving through down convert here. Whatever is being down converted with the content, I'm trying to demodulate with the signal. So when I do down convert, I should receive the signal with the same carrier frequency. So if I want to do this with the same modulation index, I have to go with the modulation index. If it is ideal modulation, I should demodulate with the ideal modulation. If it is a DSB-SC signal, I should demodulate with the same DSB-SC signal. Then I will be getting my signal back. So this is a received message. So this is a received message signal. So what I'm going to have here, how exactly I'm going to run this part, I have to keep a filter window for it to allow the signals of so much. How much filter I have to keep, passband window to do that. So now this is a demodulated portion. So now what I'll do it is I'll run once. So I'll get my signal. Do you see the initial? There is a noise. So I'll try to keep it at 20 so that you can see the change in the signal. Since though it is a simulation, so it is telling you something why there is a change in it. So I'll just take a while loop. So when you run this transmission repeatedly, so what you can do here is when you run this repeatedly, you can eliminate that errors over there. So I'll run here. So since it is not moving there, actually I'll put 21 there or 20.1. So if you see over there, so continuously moving there, so you will be getting your signal there. So that's the reason if you see, since it is very close by over there, you could not see the difference. I'll keep at 50. So you have there two different points what you have. So you can showcase it. For example, my signal is there at 100. So I have a center frequency, left side band, right side band at 100 points. So I'll go with 1000 over here. 1500. So you can see my signals over there. So this is how I have my data. So to showcase the same, what we are doing is in a smaller terms what we can keep. So you have a central frequency at 100 there. Signals are very less. So that's the reason you are getting elements over here. So actually you need to have a higher carrier frequency here. Then only you will get your signal. Do you see it is getting the signal in that way? These are all so much samples, you need to average them. You need to reconstruct them. That's the reason carrier frequency has to be more. You have to go for it. Then you will get your better signals there. So when I go for 500, I'll get a very good signal over there. So now do you see over there the changes, what you happens over there, the variations, what you get over here. So if you still want to add a noise and you want to check it, even along with the signal itself, you can add a noise and you can send. So what will happen is, so you will send over there, you will get your signal with noise. And in FFT portion, what you can do it is, instead of seeing with the linear, you can put a dB, so you can get your noise floor information there. Obviously, when you work on a channel, obviously it will have a noise there. So you'll have a noise floor, your signals are there at it. So it's a double sideband signal. You get two sidebands there. So your signal there is this magnitude of minus 60 dB there. So suppressed carrier, in the sense you don't have that. If you want to increase the strength of your signal, so your carrier frequency tone has to be on the higher end. In any queries? The same way you can do digital also. I'll just show you one example of digital. Any doubts?
Participant, if you have any queries, you can ask now. By unmuting yourself, you can ask.
Sure, sir. Because I'm really sorry, because I since it is a 1.5 hour, I have to cover maximum. So I'm just going one by one, and I'm really sorry because I got used to LabVIEW, so I'm just doing something very fast over there. But I try to keep myself with the labels clearly, with the images clearly over there, so that you can get the idea. The content, probably you will get it over there, because this we will do something as a complete hands-on session for a 5 days of program. But here it is just a 1.5 hour session, so I have to cover parts there. I'm really sorry, sir. Sure. Shall we move on to next?
You can move, sir.
Sure.
Hello, sir. One
Yes,
thing,
ma'am.
sir. This is NI based software, so everyone is not having this NI LabVIEW, right?
Yes.
So my question is, can you show something on GNU radio, which because it is open source? So can you show it now? Because see this, okay, but I have understood what is happening on this. Just with so many things are available, just combined, just like MATLAB Simulink. But thing is
Correct.
that see, many of the institutes are not having NI LabVIEW, so it will not be so useful. So thing is that, can you show something on GNU radio?
See, GNE radio, the problem is you need to have a hardware to do this, because this is just a modulation schemes what I have done. You need
Okay,
to connect a hardware. Let me check. I have a GNE radio. I had installed, but I'm not sure whether I have.
okay, no problem, sir. But
So
मतलब
in
it would be
GNE
better
radio, what
because
you can do
see,
is,
because
in
it's open
Linux,
source software
in your Linux system, when you have a GNE radio, you have a UHD option over there.
driver.
Inside UHD option, you have a transmitter and receiver where you can configure them. Then you can
Okay.
define what kind of modulation schemes you can use over there. It's a very
Okay.
similar as your MATLAB over there, ma'am. We are using
Okay.
LabVIEW platform to do it, so I'm just showcasing with LabVIEW platform. A platform doesn't make any bigger difference, because even if you use non-NI hardware also, procedure remains same.
Fine. For
Hardware
example,
platform.
I have to use this SDR radio for
Yes.
spectrum sensing in cognitive radio.
Yes.
So how I will go ahead with this?
See, that's what I said right now. Whatever I have shown here is a spectral.
That's what I'm asking, sir. See, in spectrum sensing, what we have to do, we have to observe the spectrum or whatever signals are available in the free
Correct.
space, right? So we
Correct.
are having an antenna. Antenna is capturing those signals, and from antenna,
Correct.
this will go to my RF module, and from RF
Correct.
module, I have to see, right? What
Correct.
type of signal it is. So there are various spectrum sensing methods available, like
Yes.
energy detector, cyclostationary detector method, and so on.
Yes.
So my question is,
So if
when
you
I'm
see,
using SDR, what is
first
to be
thing
done?
what I do here,
Oh, sorry, sir.
channel power, the channel power information, power and a band information, I'll do with this. Spectral measurements toolkit I have there, which I'll use with it. How exactly for MATLAB you have a separate toolboxes.
Okay,
In LabVIEW also I have a separate toolboxes to do with that.
okay. So you want to say that separate toolboxes related to power spectral density measurements are there
Yeah.
in MATLAB also.
Yes, yes, you have. So for example, if you say, if I say a power and band icon, if I keep here, I have to define the spectral information here. So if I want to look for adjacent channel power, if I want to get with adjacent channel power, I have to tell till what range I have to give for the scan.
Okay,
So I'll just simply create all controls and indicators here so that you will come to know. So if you see, I have to scan for what is the region. I have to scan for it. What elements I want to look for it. So different FFT spectrum options you can choose there. What kind of dB or linear, the same options what I shown with a single icon, which you can go for it. For example, if you see, let me take three different signals. Let me take three different signals. I'll take somewhere as one as 10, 10. I'll add a noise at 0.2. I'll take simulate signal. I'll take signal at 50. I'll add a noise. Noise is 0.3. I'll say simulate signal. There
so
is
it
no
is similar.
noise.
It
This
is
is the
similar to three different signals obtained from the free space, right? We will
yes.
consider like
Read and
this.
delete from three different devices.
Yes.
So
Okay.
this is a device one, device two, device three. In
Yes.
order to keep the strength of a signal, I'm trying to increase the amplitude of it so that the strength of a signal will be more.
Okay.
So now I'll be seeing only one output. So I'll try to combine all three together there. So three signals combined together. If I see here, I'll get three different signals of three different frequencies. Since
Yes.
one signal, whatever I have over there of much closer to it, 10 and 20, what do I have over there? Or 50, what I have there? For example, I'll keep this somewhere as 70. So now you will get two different elements what I have there in it. Or if you want to go for it also, you can have it. Anyway, I have it there, right? I'll keep 200 there. One signal, I don't have any noise added. I kept there. So you can have three different kinds of signals I have here. One is without noise, one with noise, one of little high amplitude, one is of low amplitude. To this, I'll go with this icon. I'll take a spectral measurements. So power spectral density, let me go with the dB. I'll connect here. So this is a power spectral density of all three, which will be there in a dB format. So now when I run it, I will get three different forms. If you see the signal noise flow rate minus 60 or somewhere there, one more signal does not have any noise. So it's instead of minus 150, it is moving down all the way down to minus 250. So if I want to keep them ideal with a noise information location there. So now when I run it, so you'll get 3 different peaks over there with noise elements. Now at 3 different places I'm looking. One is at 200, one is at 70, one is at 50. 3 peaks, what do I have? So this is something else. 3 different devices are giving me a signal where I'm sensing through it. Again, I'm mentioning it. If you want to view this kind of spectrum, you need to work on a spectrum analyzer to check there. This can be, for example, this we'll call it in a 5G. If you want to do something as, put it as the what direction if you want to control, where exactly you want to have your requirements are more. You need to push your data with respect to that particular receiver there. For your direction controls for elements over there, where exactly your more number of requirements are there. So multiple receivers will be there, multiple elements are there. Based on that, you can do with that. On your MIMO parts, on the other. Yes.
Okay, sir. Thank you.
Yes, ma'am. Yes, you're welcome. So this is just since I don't have a hardware with me right now, I could not show with any real data over there. But this is how the hardwares will behave there. If you go with any Tektronix spectrum analyzers or Keysight spectrum analyzers, this is how you will get it over there. And all these models you have with LabVIEW drivers there. With MATLAB drivers you have. You can work with any of your platform, whichever you are convenient with or familiar with. Yes, fine. I'll just quickly get into one more digital one, which is simple, but it will take little time over there to build up. I just want to showcase only one small portion there so that you all will understand how digital modulation schemes also you can keep in. I'll just go with the PSK modulation so that I can show UPSK, BPSK options there. I'll just go to system parameters, filter coefficients. I need a data over there, so I'll generate a data here. So these all 3 I required. So one is to define what kind of signal I need to go with, how many bits I need to go. So this is the total number of bits. So if this bits you define over there, so if you want to see that bit information, so I create indicator. So this is your output bit stream. So this output bit stream, if you want to visualize it in a form of graph, yes, we can visualize it in a form of a graph. So this bit stream, in place of simulated content, any random number, you can put this 1D array or 2D array of your content as your video or audio signal or image you can push in there. So since I'm going to do PSK, I'm going to choose PSK, M array PSK here. So what kind of normal or shifted or offset I can choose? Samples per symbol, very similar to sampling number of samples what I'm going to use. M array PSK control. So this 4 in the sense it is a QPSK. If it is 2, then it is BPSK. This M array PSK is the one which is going to define what kind of modulation schemes that we are going to do in the terms of PSK there. So whether it is differential enabled or differential disabled, that we can create here. Differential PSK, DPSK or normal, that we can define there. So one is of input bit stream. So this icon, I require an input bit stream. I require a PSK system parameter. I require a pulse shaping filter. So input bit stream is given by this generate bits. System parameter, in what way I supposed to generate. QPSK or BPSK has been provided by this system parameter option. And what kind of filter I supposed to use with it. For this number of samples to be there, I create a constant. This is also meant for PSK type where I'm going to keep. So samples per symbol also, it remains the same over here for filter. matched filter over there. So I'm going to define the filter type. So what kind of filter I'm going to use for this. So whether it is a raised cosine or root raised cosine, I can choose among there. And filter length, I can create over there for the symbols. So this pulse shaping filter coefficients, I'll feed toward symbol rate, very similar to your sampling rate, what we take. So now one icon to perform modulation, earlier we have seen. Now this one icon is performing, but along with this all we are performing there. So now if I run it for 128 bits, this is what the 128 bits. So this is for BPSK. What I'm doing, bits remain same. We have not done any modulation schemes over there. We have not done the up conversion part over there. So I'll go to RF communication, digital modulation, up convert. So this is the message. And after this icon, so I create a carrier frequency. So carrier frequency, I'll keep how good I can have my data over there. So I'll keep somewhere 300 to it. So I want to see the output. So I'll see the waveform graph here. So this is PSK. So I run here, I get error. So because symbols are very less. So I'll keep samples, 1000 bits. I'll try to keep 1024. Somewhere 64 samples per symbol I'll keep. Symbol rate is somewhere 32 I'll keep. I run. I'll maximize. This is a waveform graph for 1000 bits. What you are getting 001100 what you have, and to this you could see yeah, you could see there is a change in the element there. This is for BPSK. I'll just go for QPSK. Yes. Do you see there is a change in the elements there? This is because of the symbols what we take. For example, I'll take more number of samples per symbol. I'll get even a very good data there. Waveforms will be very proper there. This is a QPSK. Again, this QPSK, I cannot see this in forms of waveforms. There is something called as constellation graphs, which will help you about visualization of your modulation schemes. I'll just go for visualization. I'll just go for constellations. I'll just keep here. Whatever the actual data I keep, I cannot directly give this to the constellation part. I have to add a noise to it, which I will call it as an impairment. So I'll add an impairment. I'll add additive white Gaussian noise. So original data, this is the original data. Before upconvert, I feed over to this for the constellation graph. So I'll take an XY graph. So now I have to define what is the samples per symbol. Okay, you can make use of the same samples per symbol. So many number of samples to be available there. And I'll create EB by N naught. So which will be an error element. Noise. So I want to visualize this portion here. So I'll keep there. I want this to run continuous. I'll put a loop. I'll add a time delay so that it will not run very fast. So now, if you see here, I have M array PSK and EB by N naught here. I'll just keep them. I'll just keep them bigger. Okay. So now when I run this, what will happen is this is error noises are less. So once I increase this, do you see I have a 4 dots there? So now there is no filter associated to this. There is no filter associated to this. So once I add a filter to this, raised to cosine, so noises are too less or samples are less, I need to take good content, or if I want to keep BPSK, I'll get a BPSK there. So no elements are there, or root raised to cosine I can take. Or if I want to reduce it with that, only 2 elements I can take. If this is 4, I'll get there. If it is of 8, you'll get 8 points over there. So if I further reduce noises, these are all based on the symbols, how you take over here. For example, if I take a symbol rate as 16, number of samples is 32. Sorry. It's very half, right? 64. I should keep minimum. So symbol rate, I'll try to increase it by 128. Samples, I try to keep somewhere 512 I can give. So many number of samples you have for every symbol there. So lower the rate, the updates will be much faster there. Or I have to increase this bits with some higher, so that more number of samples you will have there, visualizations also will be proper. So if there is no dot, so you'll get all those points over there. So if you want keep 16 also, you can keep 16 there. So one program you can easily visualize how good you can take in it and what are the elements you can add to it. And you can push over there in it. So simple ways where you can visualize things there, how exactly you can get your informations there, you can easily move. So any doubts? LabVIEW software is not simulator. Yes, it's a simulation software. Again, once you connect hardware, it will become real time. There is no simulation in it. Without hardware, it is simulation. That's it. Yes, you can get a free version, but it is valid only for 7 days. Maximum you can extend it for 45 days by registering in a website. And I'm not doubtful. Most of the Indian engineering institutions, they have a LabVIEW software. But only thing is, it may not be a latest version. You may have a little lower version what you have over there. Many IITs, many colleges, they have a LabVIEW version. Only thing is, they were not aware whether they have a LabVIEW software in your college. Many Tamil Nadu colleges, other places, wherever I have visited throughout India, I have seen LabVIEW software over there. All colleges, Guwahati University, IITs, NITs, they all use us over there. So we have another 10 minutes. Probably we can keep this for your query sessions. So whatever queries you have, we can discuss now. I'm just done with my sessions. And one more thing I wanted to tell you is, basically for this particular hardware, if you want to keep any MIMOs, you have a very good materials over there in NA website for MIMO developments. You can easily use with multiple hardwares where exactly you can keep, how exactly you can go for your end user systems, how you can develop things, how you can test over there. You can easily use with it. For example, NA is one of the very first company who has done 128 cross 128 MIMO testbed with Nokia. NA has done it. It's something as this, what you will get it. I'll just open this page so that you will get that. So this is I'll just open this image there. So you'll get a very good big image where you can, so you can see over there your constellations. So which transmit, which antennas you are taking over there. Here you have 8 USRPs connected, and you have 8 antennas. You have this is a 8x8 system, 8 TX, 8 RX. What you have, and one computer over here, the bottom below. It's a computer PXA system, which is interfaced with this, and you have a octa clock to synchronize all the USRPs there. And this is what USRP models where you can connect different options there. NA has a very good MIMO networking platforms where you can easily work on your any 5G research or any of the research, how you can work on it, how you can connect to it, everything you can get over there. So many different types of, this is for 64 cross 64 systems. Again, it's a just an expansion of the system, what you are used with. Whether you go with this kind of setup, or whether you go with this kind of setup, or simply you use only one USRP hardware to use for your RF applications, choices is us. We can have any kind of models and we can work on it. Thank you, sir.
Thank you, sir. Thanks for sharing your valuable knowledge. Our participants has gained a lot knowledge from the lab view also, sir. Thanks for sharing your knowledge.
I'll just share my name.
Sir, please share your contact number.
I'm just sharing my, but I don't know. I cannot type
Yes, sir.
anything.
Please, thank you. One more request, sir. Actually, I am from Vivekanand Engineering College, Mumbai, and I have framed one syllabus on software radio, defined radio, and cognitive radio. So I would like to have your expert comments on that. Actually, what are the whatever contents I have chosen, whether they are good or not, and I want to see whether it will be useful for the students or not. So may I share you my syllabus for your comment, sir?
Yes, ma'am. Yes, ma'am.
So, sir, please share your mail ID so that I can mail you. And Dr. Ranjan
Sure.
Balajan from Mumbai Vivekanand College.
That's my email ID. So probably I'll just keep everything together. Yes, you can mail me here. And if you have any queries on your support required also for any 5G systems or simple SDR systems you want to plan, you can just let me know. I'll help you out with that.
Sure, sir.
You
Thank
said
you.
you have MATLAB, you can interface over there. If you see structures, do you see I have a math script where I can interface things over there. As a formula, I can directly type here. So for example, y equal to FFT of x, I can keep semicolon, done. So now here what I supposed to do it is, I have to add an input, which is x. I have to take an output, which is y. So my x will be this signal where I have to convert this into an array. So I have to feed, create numeric indicator. For example, if I take, for example, how exactly I'll create a control. So this will be the x value So I created indicators will be a Y value. So what you get there, array. So you can feed your signal and it will take off it. If you still want to use MATLAB code over to it, there is an option called as scripts and formulas, script notes, MATLAB script. Again, the same way, your MATLAB script you can directly copy and you can use it there. Even in tools also, I have a math script window over there where you can take your MATLAB script and you can push it into your LabVIEW part and you can work on it. Your entire commands you can take and you can keep them. Many options you have with LabVIEW, sir.
Participants, if you have any queries, you can discuss with the resource person.
Can we get the new version of MIMO updated? But MIMO is a method. You can use any hardware to build up a MIMO. Even if you see in my hardware also, I have a portion for MIMO interface. I have a new hardware also where you can interface with the different options there. MIMO is just a method how you are going to interface multiple hardware elements there. You can use any version of NI USRPs or any SDR hardware to build MIMO system, whether it is 2x2 or 1x2, or which means SIMO it would be 1x2 or 4x4 or 8x8 you can plan.
Participants, if you have any queries, you can discuss with the resource person now. I repeat again, participants, if you have any queries, you can discuss with the resource person.
Thank you, ma'am. Thanks. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thanks. Anybody has any USRP at your college?
Sir, shall we wind up the session, sir?
Yes, sir. If they don't have any queries, probably we can go ahead.
Participants, if you have any queries, you can discuss with the resource person. I repeat again, participants, if you have any queries, you can discuss with the resource person.
For any of your queries, if you want to write it to me, you can write it to my email ID.
So, dear coordinator, sir.
Yes.
Dear coordinator, sir, actually the feedback link is not open, so it is saying access denied.
Okay, just wait for a few minutes. I will update you.
Yes. Thank you, sir.
Oh, okay, we will update you soon.
Okay, thank you, sir.
Yes, sir. We have a 6G testbed there. Yes, we have.
A participant, like now the link is active, we may check it now.
Yes, sir. Now open, sir.
Yeah, thank you, sir.
Thank you, sir.
So this is for 5G and 6G test from NI.